Hey everyone, and welcome back to The Explainer. Today, we're diving into something absolutely fascinating. We are going to demystify the laser. Over the next 10 minutes or so, we're going to pack in the essential concepts, equations, and diagrams that take us all the way from the microscopic behavior of individual atoms right up to the tangible physical engineering of a working laser beam. It's this beautiful blend of quantum physics and optical engineering, and we're going to unpack exactly how it all works together.
Okay, let's dive into this. Here is our roadmap. 1. Pumping and population inversion. 2. Oscillators versus amplifiers. 3. Laser resonator cavities. 4. Cavity stability and types. And 5. Tuning the resonance frequency.
Starting off with Section 1, Pumping and Population Inversion. To really get this, we have to treat the atoms in our system just like fuel in an engine. We're looking at a classic 3-level laser system here. Step 1 is the intake. We use an external energy source, like a flash lamp, to basically pump the atoms from their super comfortable ground state, which we'll call E1, all the way up to a short-lived excited state, E3. Then step 2 is a quick drop. The atoms undergo this incredibly fast decay down to a metastable state, E2. Now, they don't actually emit light here. They just drop down and kind of hang out for a brief millisecond. Finally, step 3 is the spark. The atoms drop from that metastable E2 state back down to the ground state E1. And that specific transition, that is exactly where the magic happens. It triggers stimulated emission and releases that brilliant, coherent light we're after. But to make this atomic engine run continuously, we have to achieve something called population inversion. Literally, this just means we need more atoms sitting up in that metastable E2 state than down in the ground state E1. Now, because E1 is the natural ground state where atoms inherently want to be, it is heavily populated by default. So we're basically fighting nature here. It takes a massive amount of pump energy to flip that natural order and successfully invert the population. Which brings us to a really fun piece of history. The very first laser ever built, the Ruby laser using chromium ions, relied on this exact 3-level system. But, just like the first pancake in a batch, being the very first doesn't always mean being the most efficient. Because it is so incredibly difficult to achieve population inversion when your bottom level is the literal ground state, the Ruby laser required huge amounts of pump energy. It was way less efficient than the 4-level systems that engineers would come up with later on. Moving on to Section 2, Oscillators versus Amplifiers. So, the crucial point here is understanding the distinct difference between these two roles. An oscillator is essentially the spark. It's the device that generates the initial laser light right from scratch, sometimes with a tiny input signal, sometimes with absolutely none at all. An amplifier, on the other hand, is the volume knob. It does not create the light, it just takes an existing laser beam and boosts its power, drastically increasing its intensity. Simply put, oscillators create while amplifiers elevate. Up next, Section 3, Laser Resonator Cavities. Let's zoom out from the light itself and look at the physical chassis of our engine. Every single laser you will ever encounter relies on 3 functional components. First, the active medium. That's the atoms, our fuel. Second, the optical pumping arrangement. That's the energy source forcing our population inversion. And third, the resonator. Usually, this is just a pair of mirrors sitting on either end of the active medium. You can think of it like an optical echo chamber. It bounces a portion of that emitted laser light right back into the active medium for even more amplification. That feedback loop is what allows a laser to achieve steady-state operation. Now, I want to slow down for just a second here, because we are looking at the absolute mathematical heartbeat of a working laser. For a beam to actually remain trapped, bouncing back and forth between those mirrors without just escaping out the sides, the cavity itself must be mathematically stable. The condition for this is beautifully simple. 0 must be less than or equal to G1 times G2, which in turn must be less than or equal to 1. In this equation, L represents the physical distance between the 2 cavity mirrors, and G1 and G2 are special geometric parameters based entirely on the curvature of those mirrors. As long as the product of those G parameters falls between 0 and 1, you've got yourself a stable laser. Which leads perfectly into Section 4, Cavity Stability and Types. Think about the different physical mirror shapes out there that can actually trap our light. There are a couple of major standouts. Take the confocal resonator, for instance. By using two concave mirrors where the radius of curvature perfectly equals the distance between them, you get incredibly high stability. This setup perfectly supports stable Gaussian beam modes, which is absolutely ideal for precision lasers. Now contrast that with a ring resonator. Instead of bouncing light back and forth in a straight line, it uses multiple mirrors to create a continuous closed loop. That design completely avoids any back reflection into the gain medium, making it the perfect choice for highly specialized directional tools like gyroscopes. Let's actually test this out together. Grab a mental notepad because here's an interactive challenge straight from our source material. Imagine you're the optical engineer building a laser. The distance between your mirrors, L, is 1.5 meters. The radius of your first mirror, R1, is 3 meters, and your second mirror, R2, is 2 meters. Based on that cavity stability condition we just talked about, is this cavity stable? Think about how those curvature radii interact with the distance. It is exactly this kind of mathematical parameter check that engineers run every single day to ensure a beam doesn't just fizzle out.
And finally, Section 5, tuning the resonance frequency.
We've got our atoms, our pump, and our stable mirrored cavity. So how does that physical geometry dictate the actual specific wavelength of light that we see? Well, this brilliantly illustrates the connection between physical space and quantum output. Inside the laser, the cavity acts as a highly strict filter, selecting only very specific frequencies to amplify. The resonance frequency, which we represent with the Greek letter nu sub q, is equal to an integer q times the speed of light c divided by 2 times the cavity length L. What this is telling us is that the literal physical distance between your mirrors directly and mathematically selects which allowed oscillation modes can survive inside the cavity to eventually escape as a laser beam.
If you want to visualize this, personify those photons for a second. Resonance ensures that the light waves bouncing back and forth aren't just crashing into each other chaotically. Instead, they are completely in phase. They act like a perfectly timed choir, reinforcing each other over and over again to build up that incredibly strong, tightly focused output. That's what makes a laser a laser. It bridges the gap right from the theoretical math to the physical reality of a beam.
Which leaves us with this final thought to ponder. We started this explainer with invisible atoms jumping between tiny energy states, and we ended up with the precise geometry of curved mirrors. How incredible is it that by understanding and manipulating the invisible quantum math of a resonator, we literally unlock the concentrated, visible light that powers our entire modern world? From the fiber optics carrying the internet you're using right now, to the scanners at your local grocery store, it is all just atoms, mirrors, and a little bit of brilliant math. Thank you so much for joining me today. I really hope this illuminated the topic for you. And as always, keep learning.